Okay, so people are still joining after the nice coffee chats. I think triggered some discussion. Okay, so let's go directly to the second session, and we have as a first presentation, first presenter, Rodrigo Castro from ITER. And this time, of course, he will tell us about how this data is managed at ITER, in particular focus of HDF5.
Yeah.
Please.
Thank you. Okay, my name is Rodrigo Castro, and I'm technical responsible of the development of the data archiving and data handling system in ITER. I've been the leader of this project for the last 12 years. And today I'm going to present sorry. Can I do with this? Okay, so first I'm going to give you an introduction about the ITER device and the environment of our work. Then I'm going to show you some information, interesting information about our fast data archiving, which is probably the most important or technical part to be discussed. Then we are going to see the data indexing, real-time data processors, and data access services. Well, ITER machine is an experimental fusion energy device which is being built in the south of France. These type of devices are or will be ready to produce energy based on nuclear fusion. And in this case, this big device, the objective is to demonstrate the feasibility of fusion energy. So the idea is that the construction and operation of this device is not for generating energy for commercial purpose or things like that. It's more to understand the challenges, and the conditions of construction and operation of a real future energy generator. So one of the keys or one of the points, the more important point of this device, in the part of data handling, data acquisition, is that this device has to be ready for continuous operation. So in this sense, taking just about the size of this device, we can see that we have 171 plants involved in this system. And every plant has a lot of devices, diagnostics, and things like that. So in the first part of the operation of this device, we are going to start with more than 200,000 signals, where we are going to have fast data acquisition, basically diagnostic and fast control. We are going to have more than 1 million of variables for slow control, and about 2,000 variables for our real-time network. Basically, what we are seeing is a very complex infrastructure with huge number of variables and signals to measure of different types of data. This is normal, okay, in this type of complex devices or experimental devices. The nature of the plasma is chaotic, so it's very important and requires very high sampling rate, very fast data acquisition systems with high data throughput. This is until here, more or less normal, but with very big plus, which is long pulse and continuous operation. And this has been really a big challenge for us. This is the key point of our work. because comes a new dimension, which is very complex from data handling point of view. For managing time evolution signals, where timestamp is critical, on-flight change of data properties, data acquisition groups or diagnostics groups require different sampling rate along the acquisition, require change of dimensionality, resolution of the cameras, things like that. So the characteristics, the properties, core properties of the data can change on fly. And of course, real-time data archiving and handling. This is necessary because the pulses, the experimental pulse will be half an hour, but the system, data handling and data acquisition system must be ready to operate in continuous mode. So this is the requirement, this is the challenge, and is how we have been designing and implementing this system. Well, basically, for fast data acquisition archiving, this is very simple, just very brief schema. We have as controllers about the different plant systems, which are acquiring, are measuring, producing data, and they are going to distribute on fly continuously data to the data archivers on remote. Basically, this is the architecture. In more detail, we have the client part of fast data acquisition, and this is the server part. In the client part, what we are providing is an API that simplifies the job of acquiring and publishing data to be archived. So we provide this API for diagnostic developers, and they put the data, and the API, the library, do all the job for them. So takes the data, put it in the correct sequence, and distribute to the servers to be archived. And finally, all the data is being archived in HDF5 files. This is the base technology that was selected for this purpose time ago. Basically, the API, just for information, can operate in 3 modes. One mode that the buffer and the data are located in the data acquisition hardware, and the API only notifies when and where the data is available. But all the data is retrieved from the hardware device, data acquisition device. In other modes, depending on the data acquisition hardware, the API provides the possibility to have an internal DAC buffer, but is responsible to take the data, or this buffer is used as DAC buffer for the data acquisition hardware. So the transmission of the data, let's say, is not responsible of data acquisition software. And in the third mode, the API provides all functionality, and the data acquisition software is responsible to do all the job of putting the data, notifying, do all the things. The API provides all these functionalities, all these features, and also is responsible to distribute the data to the data archivers on remote. Well, in this fast data acquisition, we have data from 2 kilohertz until gigahertz. The speeds that we are managing avoids the use of 1 timestamp per sample. This is impossible in our case. And data acquisition or diagnostic developers that develop the data acquisition systems or software usually put the data in blocks. Takes a block of data and assign that timestamp for all that block. Usually it's not the way to establish 1 timestamp per sample. And this data archiving system supports multi-channels like data acquisition cards, following the same schema. And basically all our system, one basic and key component is the data block. Data block is the unit which is coherent, has associated metadata that make all the data which is contained coherent with the same sampling rate along the block, same dimensionality. So these properties can be changed between data blocks, but in the same data block, all these properties must be coherent, must be the same. One time stamp per data block and contains complete samples. So it's not possible to break samples between data blocks. This makes the data block the most coherent and basic unit of all of our system. And this makes the system also flexible because between data blocks, you can change this type of sampling rate or dimensionality of the data and other things like metadata. So basically, this is the protocol. Dan protocol Dan is that archiving network, is the network which is used for fast data acquisition. And what is transmitted from the clients to the server is some metadata associated with a stream of data, a time period of data, user-defined data types, channel information about the different channels which are being acquired, and then the data blocks with the timestamp, with the information, with header, and interleaved data for all the channels which are involved in the data acquisition. Then inside one of these samples, the format is very rich. You can have different dimensionality, you can have compound data types, you can have many combinations of data type. But this is the structure. And the way of archiving this type of data is basically the stream metadata, the metadata associated with the channels, related with the information like units, like calibration, things like that. And then two data sets, or two main data sets, block headers, which are archived in one data set, and the payload. And the payload is archived in one data set, all the payload. So basically, these block headers are working also as internal indexing, or where is the payload associated with a block header. When we need to locate some data in the file, what we have to do is do first work in the block header data set, and this gives us the position and location of the associated payload. But the first work, the logic, is made here, not here. This is just for retrieving the data. Well, why we have done this? Basically, as I said, we are working with two data sets, data blocks and payload. The use of this data block data set speeds up data allocation and give us the flexibility of changing sampling rate and dimensionality along the data acquisition. In this way, we can change the properties of data acquisition, and their data contained during a data acquisition is not forced to be completely fixed, the sampling rate, the dimensionality. We provide this capacity, but the way to do it is based on the data block concept. Another point is that the data block and payload must be archived as is received. The data acquisition speeds that we are working with and the length of the pulses, the length and the characteristic of continuous data acquisition system have shown us that it's not really possible to be processing data when it's received. As much as we can do is to archive it as it is, and is enough for us. So this is the job that we can do when basically if we have small data blocks, what we do is to do a buffering before archiving to decrease the number of writings. Because when we have tried to use small data blocks, because by any reason the data acquisition is doing that, produce a very high CPU usage, writing a lot of data blocks, a lot of elements in the data sets. Even using chunking technology is not really efficient for us. So this is the challenge. Even for data acquisition groups, in some cases, we have to handle with data which is coded in a very extremely way. For example, in 64 bits is coded a lot of information, which basically is an opaque data type. It's not really a standard, or it's breaking the philosophy of HDF5, which is the data must be in a standard format, accessible, well, not in opaque data types. But data acquisition is like that. A group develop a FPGA or whatever, and because efficiency or performance, they need this type of codification in 1 or in 8 bytes or whatever. But from our system point of view, data handling, we have to provide more standard formats, more standard mechanisms. We cannot open the Pandora box of, okay, let's accept any type of opaque codification for different data acquisition groups, and people can send us the data in many ways, and our system will adapt, and we will provide strange things for this type of data. So a solution that we have seen for these special cases is not the typical, but some special cases, is the use of HDF5 filters that provide us a solution to let our readers to see the data as normal data. Even if it's coded in a very special way, our readers see HDF5 formats like typical fields and standard data types. So we didn't need to change our readers for these special cases. And regular data sampling rate and extractor speeds up data access. When we have regular portions of data with regular sampling rate and regular structure, we have got much faster data access than when the data is with different sampling rate or structure, because it's much easier to pick up samples when you have regular data. So we have created something that helps us a lot, which is time sections and structure sections. Inside the file, we define this type of sections, and inside the section, we speed up a lot the data access. For indexing, we have an infrastructure that in real time, we are creating a catalog at first level with information which are in the files, and is responsible of detecting data storage events, indexing data which are in the file, metadata, basically, and inject this data into index info database. This is the infrastructure. We have listeners that detects the file system events, indexers that works in parallel over the large-scale file system, and injects the information in our info database. This is the structure of our listeners that basically do this job, simple job of watchers. And this is the indexer engine that are continuously checking for new works to index, new files to be indexed, while they are being created in a storage file system. And we have a set of plugins that adapt to the different types of data, extract information, and inject the information into our index database. In this part, we have critical system for long polls and continuous data acquisition. This is a critical part. If you don't have this part, you are lost. File system events, we have seen that it's a good notification mechanism to detect for new files or closed files, things like that. Not very complete. Sometimes we have to be very careful not to lose some of these events. And sometimes the distributed file system does not support correctly this type of file system events. So, well, but it's good, it's correct, it's good. It's not a bad way of doing it. We have created, or it's necessary for this type of indexing to react very well or to have very good reaction policies for non-ready files, because the file is created and there is a stage where the file is not ready for being indexed. It's just being filled with metadata, with a structure. The file is open for the file system, but it's not really in a correct state for being indexed. So it's necessary to manage this type of things. Also, the indexer system is very good friend for detecting wrong data files, because these files or this type of data files are very dangerous for the system, because damage the logic, destroy, halts the data access systems, all these things. So very important to detect this type of things as soon as possible. And also to detect, for example, orphan open files that for any reasons has not been closed correctly. So other element that we have is the real-time processing. We process archive data in real time. As they is archived, we process the data sometimes. And follows the same high scalability model as indexer with multiple instances in parallel. Implements a generated architecture for real-time data processing development and supports calibrated data. This is the architecture of this type of component that basically is able to expand automatically all the components when reads the file. So the text structure of the file, open the components for real-time processing, and every of these elements do the job of processing the data. Why we use this type of processors? For example, for replication. We use one of these elements to replicate the data to external file system or remote. Because in this type of models, HDF5 models, is not only to copy. You cannot do the copy of the file. You need to create at the other side, in the other file system, coherent data. To create coherent data, you have to control this replica process. The data sets must be replicated correctly, in the correct order, in the correct sequence. And when the remote file is being created on fly, continuously this data must be current. All data sets, everything. So the replication must be done in this way. And downsampler, because the data access for huge amounts of data at very high sampling rate is awful. Even a very simple mechanism like, okay, please give me 10,000 values from this time to this time. And imagine, detect the files, the amount of data is so full, you have to select which values are the best ones for that interval, extract them. Is really complex operation. So what our strategy is to do a look ahead philosophy and try to downsample the files if it's possible before, or as much as possible. So in our data access service, we support different data types. We request by time interval. We manage metadata, payload, dimensionality, data chunks. Let me focus on, yeah. This is the language for requesting data. Sorry, this is the language that we use for detecting, for requesting data in our time system. Basically, we define the variable we want to get, the interval in very different modes, with absolute or relative timestamp along an event, along a short, a pulse, and we can, or we provide different modes of returning the data. This is the syntax that we use in this type of request, and what we have seen is that this type of request language is very powerful for this type of time evolution data requests. It's able to implement complex time evolution data requests, is intuitive for users or for developers, and is very extensible. It's very easy to extend with this type of. And just the key component of this type of data access system, one of the key components is the detection of the best files to cover a requested time interval. Basically, is to locate the involved files, to select the files that best fit the requested data resolution. If you have different versions of the data at different sampling rates, because you have done a job of downsampling previously, you can select which is the file that best fit the requested time resolution for that request. Also, the system has to be able to manage overlaps. Sometimes you have different files for the same time interval because you have replica of the data or things like that. And it must be able to integrate already open files because are valid for the request many times. And just the next things to cover in future, data sanity check improvement. We have to push in this part because to detect wrong data is very important for the system, and to see if some data is really valid or not. Files version support, trying to avoid copy. So in our case, we are trying to use HDF5 external links to create versions of the data files without copying. Improve data access protocol for long intervals. In this case, this type of mechanisms of protocols that give us chunks along the times, things like that. And in the case of massive data access, to create advanced massive data access mechanisms like automatic detection of interesting points in the data for users to help them to detect which parts of the data are interesting for them. Imagine a video of half an hour was to detect something interesting inside. Advanced decimation mechanisms, just one of n sometimes is not enough, and we have to provide decimations that give the user better knowledge of the shape of the signals and things like that, not to look peaks, things which are interested for them. And, or for example, automatic patterns search in the data. And thank you very much. That's all.
Rico, I think we have time for one question. Yeah.
Was the mirror VFD not useful for copying a file to another remote system? Are you familiar with the mirror VFD?
Sorry?
Mirror VFD in HDF? We can copy a file to a remote system.
You have a mechanism?
Yeah, mirror VFD.
Yes. Yes, exactly. This type of step is a step ahead to create this type of coherent copy of the HDF5 file. But sometimes there are internal logic that also must be coherent for you, not also. It's true that, but imagine, for example, if I have a data block data set and I have the payload, there is an internal rule in my logic that must be preserved, which is payload must be before than the block header, always. If this is not possible to achieve, the data will be broken because it's not current to have the data block header if you don't have the payload. So things like that are very difficult to be controlled automatically if you don't establish some rules or things that relate your data sets or groups or things. So would be this type of sync software or sync logic, but requires some extra logic internally, like creation this type of relation rules that helps the synchronization, like mirroring, to do the job for us, because this type of logic is necessary. It's not, if it would be just one data set, perfect. But the problem is that usually you have different data sets and you have to keep this internal logic. So.
Okay, thank you. Let's thank you, Rodrigo, again.